Hello my fine people, I hope you had a fantastic day. Recently I was finishing some experiments and so I started doing some initial data analysis, with which came some unexpected results, and while checking for the cause of those problems, a question came to me. Do you trust computers? We're all used to computers being precise, right? Especially when it comes to calculations. I mean, when was the last time you questioned the results your calculator gave you? Most of the time when something goes wrong, it's user error. But what if I told you computers make mistakes as well? And not only do they make mistakes, they do it in subtle, fascinating ways. Though they often give rise to a lot of frustration. But if we want to get the most out of our experiments, we need to tackle them, and for this we need to know what sort of errors exist and what causes them. So let's talk errors. From spilling coffee to mixing up your calendar, errors sneak into everything we do. Usually we just clean up and move on. But when errors happen in science or in computers, the consequences can get quite interesting. When scientists run experiments, there are always uncertainties. Maybe your measure is slightly off, or the signal frequency isn't quite what you needed. Or maybe a chair brushes against your big, expensive machine and you lose a week trying to figure out where the noise came from. Ask me how I know. These are experimental errors, and they usually fall into two groups, random errors and systematic errors. We deal with them using statistics and calibration, doing more measurements to average things out or fixing faulty setups. But even after the experiment is done, we are not free from the yoke of errors. Next come computational experiments and analysis. You might think computers are precise, after all they are made for calculations, yet computers can make errors too, because of how they represent and process numbers. These mistakes can affect everything, from data analysis as mentioned, to weather simulations, to even sending spacecraft to Mars. As you know from everyday life, there are many different errors or mistakes that can happen. Though we are focusing on the computational ones, there are still many types of errors, so dealing with them can be quite overwhelming. But we can make our job a bit easier by grouping them together by some common characteristic. There are many ways to do that, and here I'm choosing an arrangement based on their sources, collecting them into 4 sets: blunders, random errors, algorithmic errors, and rounding errors. Naturally, there is some overlap between them, but let us start. Blunders, also known as gross errors. They are the human touch in computational errors. They are not the fault of the computer, but of the human, being the user or programmer. But we still need to be aware of them, and to check when we encounter some strangeness. Blunders are varied. A typo in the code, like using a plus sign instead of a minus sign, logical errors, when the code runs but performs the wrong calculation because the underlying formula is wrong, a misplaced decimal point when entering initial input data, or the wrong unit, so you move the instrument 1 meter into the sample instead of 1 nanometer. Again, ask me how I know. Everyone who's ever programmed knows this pain, both beginners and experts alike. And while they seem simple, the consequences can be enormous because the computer, following the flawed instructions to the end, can churn out completely nonsensical results with absolute confidence. So, how do we deal with them? The fix for blunders lies in establishing rigorous checks and processes. It's a two-pronged approach. First, we do a careful code review and debugging. This involves carefully going through the code's logic and using debugging tools to inspect variable values. This is to ensure that the program is doing what you think it's doing. Peer review is also critical, as a fresh set of eyes can often spot the most obvious errors. The next thing is robust input and output validation. This means writing code to check the data before it's processed. For example, ensuring that you don't divide by 0, an input value is within a sensible physical range, or that the final result passes a basic sanity check, like you don't calculate the mass of the electron to be a couple of kilograms. By implementing these safeguards, we can dramatically reduce the chance of small human oversight leading to major computational failure. Next up, random errors, also called stochastic errors. They are the ones that emerge after your code is validated and seemingly bug-free. When your program is running smoothly and it suddenly spits out a completely nonsensical result, like water freezing at 512 degrees Celsius, you have likely encountered a random error. Unlike blunders, random errors are unpredictable and usually stem from temporary, non-deterministic physical phenomena. Here we have things like hardware instability. The classic example is single event upsets. This happens when a high-energy subatomic particle, such as a cosmic ray, strikes a transistor in a memory chip or CPU. The energy can temporarily flip a bit's state from 0 to 1 or 1 to 0, altering the value in memory, like in the famous Mario 64 speedrun. Another possibility are race conditions. This is a bit of an overlap between blunders and random errors. In complex, multi-threaded or distributed programs, two or more operations might try to access and modify the same data simultaneously. Even if the code is logically sound, the precise, uncontrolled timing of these events can lead to a random, incorrect result. Love you. The defining feature of random errors is that if you run the exact same program with the exact same input data 10 times, you might only see the error once, and it will likely occur at a different point in the computation each time. They are not reproducible. This is what makes them so difficult to debug, and they tend to follow statistical distributions. While a single event is unpredictable, the frequency of these errors across a massive number of runs often follows known patterns. So how do we deal with them? You can't code your way out of a cosmic ray hit, obviously, so the fix for random errors is a mix of engineering and statistics. First, we can use ECC memory. Most high-performing computers use the error-correcting code memory, which adds extra bits to data chunks. These extra bits allow the system to detect single-bit flips and even correct them automatically, effectively mitigating the effects of a single event upset. The methods that are employed here I find quite fascinating, and if you want, I can talk about them in detail in a later video, so leave a comment below. In addition, there is triple modular redundancy, where in critical systems, like spacecraft, the same calculation is performed simultaneously on 3 separate processors. If one result differs, the other two vote to determine the correct value, disregarding the one affected by the random error. In addition, we can do statistical methods. Since these errors are random, we must run calculations multiple times and use statistics to find the most probable correct answer. If one result is very different, for example the 512-degree ice, we treat it as an outlier and discard it, averaging the remaining results to get a more reliable answer. These techniques don't prevent the error from happening, but they limit the impact on the final calculated result. Now, our next category are algorithmic errors. As you might expect, they arise due to imperfections in the algorithms we use. But the interesting thing is that we sometimes use these flawed algorithms on purpose, even though better ones exist. We pick algorithms that trade accuracy for speed. Think of it this way. Your computer is facing a complex mathematical problem. It can use an extremely complex method that takes 10 seconds to give you the perfect answer, or it can use a shortcut, an approximation that takes 0.1 seconds, and gives you an answer that is close enough. I mean, do you really need to know your GPS location with the precision of a tenth of an atom? Probably not. An answer that is accurate to a few meters is perfectly fine, and it allows your navigation app to run in real time. Similarly, approximating a square root or calculating a complex trigonometric function with fewer steps can make a massive, detailed game run very smooth. It's a deliberate design choice. We call these methods numerical methods or approximations. The error we introduce is called the truncation error because we are essentially truncating the full infinite mathematical procedure into a finite manageable number of steps. It's a balance, speed versus precision. Go too fast and you miss the target entirely. Go too slow and well, your computer might start complaining and your app will be unstable. The key is to know how much error you can tolerate and pick the fastest algorithm that stays within the boundary. And finally, my favorite type of blunders, rounding errors. As computers can store infinite digits, they only have a finite amount of memory for every number. So, when you calculate something like the exact fraction 1 over 3, which in decimal is 0.3333 repeating forever, the computer has to cut it off at some digit, depending on the format. Each tiny rounding might seem harmless, an error far too small to matter, but when you do millions of calculations which happen every millisecond inside a CPU, those small individual errors can suddenly add up. This can lead to whole simulations spiraling out of control. This accumulation is unpredictable, and this is why I like it so much. There are a lot of interesting statistics and analogies that we can make, one being a random walk. Each rounding is a small push from the start location, but over a massive amount of steps, it slowly drifts away. The core issue is limited storage. In big simulations, we have to choose how much memory to dedicate to precision. Do we need doubles, more precision and more memory, or are floats okay? Are 8-bit integers enough, or do we need 64-bit? This is a constant computational dilemma. Luckily, there are some clever tricks and mathematical methods that you can use, like extended precision or Kahn summation. And that is exactly what I would like to explore in one of the next couple of videos. So if that deep dive into fixing these errors sounds interesting to you, hit the subscribe button and like the video. And let me know down below in the comments what was your first experience with computational errors. Have fun and see you next time.